Right now, more than 500 light years from where you're sitting, two entire worlds are coming apart in front of humanity's most powerful telescope, and scientists are watching it happen in real time. Not a simulation, not a computer model predicting what might happen millions of years from now. Actual, live, ongoing transformation captured directly by the James Webb Space Telescope, showing two separate planets shedding enormous clouds of their own atmosphere into space, one of them wrapped in not one but two colossal streams of escaping gas, the other trailing a cloud so massive it now travels ahead of the planet itself, like some enormous invisible shield being torn away and flung forward into the dark. Scientists studying this data are calling it the most detailed portrait ever captured of a planet actively transforming under the direct control of its own star. This is that story. And once you understand exactly what's happening to these two worlds, you'll never look at a distant point of light in the night sky quite the same way again. Let's start with the first of these two worlds, a planet called WASP 121b, because its story sets up everything else you're about to hear. WASP 121b belongs to a category of exoplanets astronomers nickname ultra-hot Jupiters, gas giants roughly the size of our own Jupiter, but orbiting so close to their host star that a single year, one complete trip around their sun, takes less time than a single day here on Earth. WASP 121b's entire orbit lasts just 30 hours. 30 hours to complete an entire year. It sits so close to its parent star that its dayside temperature regularly exceeds 2,500 degrees Fahrenheit, hot enough to vaporize metal, hot enough that iron and other heavy elements exist in its atmosphere, not as solid particles, but as gas, drifting through skies more violent than anything found anywhere in our own solar system. In late 2025, an international team of astronomers led by researchers at the University of Geneva, working alongside the National Center of Competence in Research Planets and the Trottier Institute for Research on Exoplanets at the University of Montreal, pointed the James Webb Space Telescope at WASP 121b and did something nobody had ever successfully managed before. Instead of a single quick snapshot, the standard method astronomers typically rely on, the team continuously monitored the planet's escaping atmosphere across its entire orbit, tracking exactly how it changed, minute by minute, hour by hour, as the planet swept around its star. What they found, published in the scientific journal Nature Communications, stopped the entire team in their tracks. WASP 121b isn't losing its atmosphere in one simple, predictable direction. It's surrounded by two separate colossal tails of escaping helium gas, extending outward across more than 60% of the planet's entire orbit around its star, and structures so large and so persistent that it dramatically reshapes how scientists now think about what atmospheric loss on an extreme planet like this actually looks like. To understand why two tails is such a strange, significant finding, you need to understand how astronomers normally expect atmospheric escape to behave. When a planet orbits close enough to its star to lose material to space, standard models predict a single trailing tail, gas blown backward relative to the planet's direction of travel, similar to how a comet's tail always points away from the sun. That's the picture astronomers carried into this observation. WASP 121b broke it completely. Webb's data revealed helium streaming away from the planet in two distinct directions simultaneously, one trailing behind the planet as expected, but a second, equally massive stream extending the opposite way, essentially creating a structure that wraps around a significant portion of the planet's entire orbital path. Vincent Burrier, one of the lead researchers on the study from the University of Geneva, described the result plainly. New observations like this one frequently reveal the limits of existing scientific models, pushing researchers to explore entirely new physical mechanisms just to explain what they're actually seeing. In other words, this isn't a case of confirming what scientists already expected to find. It's a case of Webb catching a planet doing something nobody's models predicted was even possible. Before we get to the second planet, it's worth sitting with just how strange WASP 121b already was to astronomers, even before this new discovery. The planet was first identified back in 2015, and researchers have spent the years since building an increasingly extreme portrait of its environment. Its atmosphere doesn't just contain the usual mix of hydrogen and helium found in most gas giants. It contains detectable amounts of vaporized metal, iron, and magnesium existing as gas in its upper atmosphere, something astronomers had only ever previously observed indirectly through subtle shifts in starlight passing through the planet's atmosphere during a transit. WASP 121b's dayside is locked in permanent, blistering daylight, while its night side remains in permanent darkness, the planet's rotation tidally locked to its star, the same way our own moon always shows Earth the same face. That extreme temperature difference between day and night sides drives ferocious winds, some of the fastest atmospheric winds ever measured on any planet, funneling superheated gas from the scorching day side toward the relatively cooler night side in a constant, violent cycle. This was already one of the most extreme, most closely studied planets known to science before Webb's continuous full-orbit observation revealed its double helium tail, which tells you something important about just how significant this new finding actually is. Even a planet astronomers thought they already understood in detail still had a fundamental surprise waiting to be found. Now, here's where the second planet enters the story, and where things become genuinely unsettling, because this isn't an isolated one-off event happening to a single unlucky world. It's part of a pattern. Just weeks after the WASP 121b findings were published, a separate international team led by researcher Vigneshwaran Krishnamurthy at McGill University, working with scientists from the University of Geneva, the University of Chicago, Cornell, and Johns Hopkins, published a second, equally dramatic discovery in the journal Nature Astronomy, this time focused on an entirely different world, WASP 107b, a planet sitting more than 210 light-years from Earth. WASP 107b belongs to an even stranger category of exoplanet. One astronomers have started calling superpuffs, gas giants with a mass similar to Neptune but a radius closer to Jupiter's. Essentially, planets so extraordinarily bloated and low density that some of them would technically float on water if you somehow found an ocean large enough to test it. Using Webb, the team detected an enormous continuous cloud of helium gas evaporating directly off WASP 107b's surface. And the scale of what they found genuinely surprised even the researchers who spent months analyzing the data. The escaping gas cloud around WASP 107b stretches nearly 10 times the planet's own radius, an almost incomprehensible distance when you actually try to picture it. A cloud of escaping atmosphere roughly 10 times larger than the entire world it's leaving behind. And here's the detail that made this discovery genuinely historic. This escaping material doesn't just trail behind the planet the way scientists expected. It actually precedes WASP 107b along its orbital path, streaming out ahead of the planet as it travels, essentially meaning the planet's own lost atmosphere is now leading the way through space in front of it, visible proof of just how violently and continuously this world is being stripped apart by the radiation pouring off its host star. Researchers confirmed this represents the first time Webb has ever directly observed a planet's atmosphere evaporating this extensively, in this much detail, using an element, helium, that has become one of the most powerful and reliable tracers scientists have for detecting exactly this kind of atmospheric escape. WASP 107b has its own strange backstory too, one that makes this new discovery land even harder once you understand it. Astronomers have been fascinated by this planet since long before Webb ever pointed toward it, precisely because of how impossibly light it is for its size. With roughly the mass of Neptune, but a volume closer to Jupiter's, WASP 107b has an average density lower than nearly any other planet ever discovered, so low that researchers have spent years trying to understand how a planet this fluffy, this loosely held together, could have ever formed in the first place, let alone survived this long in such close proximity to its own star without being torn apart completely. Earlier observations using Webb, published back in 2023, had already revealed an unusually complex, layered atmosphere on WASP 107b, containing water vapor, sulfur dioxide, and even clouds made of fine, sand-like silicate particles suspended high in its skies, an atmospheric chemistry unlike almost anything else previously cataloged. This new 2025 discovery of its enormous forward-streaming helium cloud adds an entirely new, more urgent layer to that picture. A planet already famous for being extraordinarily fragile is now confirmed to be actively, visibly disintegrating, its atmosphere quite literally leading the way ahead of it through space as radiation continues tearing it apart. So why is this actually happening, and why now, to two separate planets, discovered within weeks of each other? The underlying physics connecting both discoveries comes down to one simple, brutal fact. Proximity to a star is dangerous in ways that unfold slowly, relentlessly, over the entire lifetime of a planet. Both WASP 121b and WASP 107b orbit extremely close to their host stars, close enough that intense radiation, including high-energy ultraviolet and X-ray light, constantly bombards their upper atmospheres. That radiation heats the outer layers of gas surrounding each planet to the point where individual particles gain enough energy to physically escape the planet's gravity entirely, boiling directly off into space, in a continuous, ongoing process scientists call atmospheric escape. It's not an explosion. It's not a single catastrophic event. It's a slow, grinding, continuous erosion happening every single second, gradually and permanently, reshaping each planet from the outside in. And it's worth understanding that this process doesn't just happen to distant, exotic worlds light years away. Even Earth loses a small amount of its own atmosphere to space every single second, primarily lightweight hydrogen gas drifting away into the vacuum, at a rate scientists estimate around 3 kilograms per second. Earth's escape is slow enough, and our planet's atmosphere thick enough, that this loss has essentially no meaningful impact on life here. not across any timescale that matters to us. But WASP 121b and WASP 107b sit so close to their stars and receive so much more intense radiation than Earth ever experiences from our own sun that the exact same fundamental physical process becomes dramatically, visibly accelerated, transforming from an invisible background process into something powerful enough for a telescope 1 million miles from Earth to directly photograph from hundreds of light years away. Here's the part of this story that should genuinely give you pause, the part that turns this from an interesting discovery into something closer to a warning written across the galaxy. Scientists studying both of these planets describe atmospheric escape as a process capable of profoundly transforming a planet over time. And they mean that literally, not poetically. A gas giant, losing enough of its outer atmosphere over millions or billions of years, doesn't just get slightly smaller. It can fundamentally change categories entirely, evolving from a puffy, atmosphere-rich gas giant into something denser, smaller, and structurally different, an entire class of planet potentially being created through nothing more than sustained, continuous radiation stripping away everything except a dense, stubborn rocky or metallic core. Some scientists believe this exact process may explain a genuinely strange gap astronomers have observed in the broader population of known exoplanets across the galaxy, a noticeable scarcity of medium-sized planets sitting in a very specific size range, as though something is actively preventing planets from staying in that middle zone for very long, either pushing them to hold onto a thick atmosphere permanently or stripping them down entirely into something smaller and barer. WASP 121b and WASP 107b may be humanity's first real-time look at exactly this transformation happening live, caught mid-process rather than reconstructed, after the fact from planets that finished changing millions of years before any telescope existed to watch. Think about the scale of what Webb actually managed to capture here. WASP 121b's double-tailed structure required continuously monitoring the planet across its entire 30-hour orbit, an extraordinarily demanding observation requiring the telescope's full attention, uninterrupted, for longer than a full day, tracking subtle shifts in light as helium gas absorbs specific wavelengths passing through it. WASP 107b's leading gas cloud, stretching 10 times the planet's own radius, required detecting an incredibly faint signal, helium absorption spread across an enormous volume of nearly empty space. A signal so subtle that no telescope before Webb possessed the combination of sensitivity and precision necessary to detect it clearly. Both discoveries depended entirely on capabilities that simply didn't exist before this exact telescope, positioned 1 million miles from Earth, launched at the end of 2021 after decades of development, finally came online. And both discoveries arrived within weeks of each other, a detail astronomers involved in this research consider genuinely significant rather than coincidental. Finding one planet undergoing dramatic, structurally significant atmospheric escape might be written off as a rare, unusual case, an outlier world with some unique quirk explaining its behavior. Finding two, in two completely separate planetary systems, using two independent research teams, published in two separate peer-reviewed journals within the same short window of time, suggests something much bigger. That this kind of dramatic, ongoing planetary transformation might be far more common throughout the galaxy than anyone previously assumed, simply invisible to humanity until an instrument powerful enough to actually witness it finally launched. There's a broader technological story behind both of these discoveries too, one worth understanding because it explains why findings like this are only becoming possible now, decades after astronomers first started suspecting atmospheric escape might be common throughout the galaxy. James Webb Space Telescope carries an instrument called NIR-SPEC, a near-infrared spectrograph capable of splitting starlight passing through a planet's atmosphere into an extraordinarily detailed rainbow of wavelengths, precise enough to detect the specific chemical fingerprint of helium and other elements as that light filters through gas escaping the planet. Ground-based telescopes and even Webb's predecessor, the Hubble Space Telescope, simply lacked the combination of sensitivity, wavelength coverage, and stability in space necessary to detect signals this faint, spread across structures this enormous, without the effect getting lost in noise or blurred by Earth's own atmosphere. Both of these discoveries represent years of technological development finally converging with two planets, whose extreme, close-in orbits happen to make them ideal natural laboratories for testing exactly what this new generation of instruments could actually detect. Researchers involved in both studies have been careful and appropriately honest about how much remains genuinely unknown here. Scientists still don't fully understand why WASP 121b's escaping gas splits into two distinct tails instead of the single trailing stream existing models predicted, and they've openly stated that future Webb observations will be essential just to determine whether this double-tail structure is some kind of unusual exception or a common, previously undetected feature hiding throughout the broader population of hot exoplanets across the galaxy. Similarly, the team studying WASP 107b has acknowledged that watching a planet's escaping atmosphere physically overtake and precede the planet itself along its orbit raises fresh questions about exactly how these gas clouds interact with stellar radiation pressure and the surrounding environment. Questions current models simply weren't built to answer, because nobody had ever directly observed this exact behavior clearly enough to know it needed explaining in the first place. There's also a deeper, quieter significance buried inside both of these discoveries, one that extends well beyond these two specific planets. Astronomers have spent nearly 3 decades cataloging thousands of exoplanets across the galaxy, and one of the strangest patterns to emerge from that entire catalog is something researchers call the radius gap, or sometimes the Fulton gap, a noticeable, statistically significant scarcity of planets sitting at a very specific intermediate size, roughly 1.5 to 2 times the radius of Earth, as though something is actively preventing planets from comfortably settling into that particular size range for very long. For years, the leading explanation has been exactly this kind of atmospheric escape. The theory that planets forming with a thin, puffy hydrogen and helium envelope in that size range either get stripped down entirely into smaller, denser rocky worlds, or somehow manage to hold onto a much thicker atmosphere and remain larger, gas-rich worlds instead, with almost nothing surviving comfortably in between. WASP 121b and WASP 107b are far larger, far more extreme planets than the ones directly responsible for that particular gap, but every confirmed, directly observed case of dramatic atmospheric escape adds real physical weight to the broader theory, moving it from a purely statistical pattern in a catalog towards something scientists can now actually watch happening, live with their own instruments. Every single confirmed case of atmospheric escape gives scientists another real physical data point for understanding how planetary atmospheres evolve over cosmic timescales, information directly relevant to one of the biggest open questions in modern astronomy. Which planets throughout the galaxy might actually be capable of holding onto an atmosphere stable enough and thick enough to potentially support life, and which ones are destined to be stripped down to bare, hostile rock long before anything resembling life ever had a chance to take hold. Understanding exactly how and how quickly radiation from a nearby star can physically dismantle a planet's atmosphere directly shapes how astronomers evaluate the habitability of every new exoplanet discovered from here forward, including smaller rocky worlds sitting in the potentially habitable zones of their own stars, worlds far more likely to actually matter for the search for life beyond our solar system. There's also a striking visual way to actually picture what's happening around each of these worlds, because the numbers alone can be hard to fully grasp. Imagine standing on the surface of WASP 121b, if such a thing were even remotely survivable, and looking up to see not one but 2 enormous plumes of your own planet's atmosphere stretching away in opposite directions, curving out ahead of and behind you as you orbit, visible evidence of your entire world's substance being pulled apart and scattered across space in real time. Now imagine WASP 107b instead, where the escaping material doesn't trail behind at all, but instead races out in front, meaning if you could somehow watch the planet's journey from a distance, you'd see its own stolen atmosphere arriving at each point in the orbit before the planet itself does. A genuinely strange image once you actually let it sink in. An entire world being consumed from the outside in, its own vapor announcing its arrival before it gets there. It's worth being clear about one more thing here, because responsible reporting on genuine science requires it. Neither WASP 121b nor WASP 107b poses any conceivable threat to Earth or to anything in our own solar system. Both planets sit hundreds of light years away, orbiting entirely different stars, and the physical process destroying their atmospheres, intense radiation from an extremely close host star, simply doesn't apply to any planet in our own solar system in anything close to the same way. This isn't a story about danger reaching toward us. It's a story about danger already fully underway somewhere else entirely, captured with a level of clarity and detail humanity has never achieved before, using a telescope that took decades to build and that continues, discovery after discovery, to reveal a universe stranger and more dynamic than the one scientists thought they understood before it launched. So when you hear that James Webb detected 2 planets entering a terrifying transformation, understand exactly what that footage really represents, and understand too that this is very likely only the beginning of a much longer list. Both research teams have already indicated plans for follow-up observations, and astronomers across the field are now actively re-examining other known hot exoplanets with fresh eyes, wondering how many more worlds out there are quietly undergoing the exact same kind of dramatic transformation, simply waiting for someone to point Webb in the right direction long enough to notice. It's not science fiction, and it's not exaggeration for the sake of a headline. It's 2 entire alien worlds, caught by humanity's most powerful telescope in the actual, ongoing process of being reshaped by their own stars, atmosphere by atmosphere, one enormous helium cloud at a time, unfolding right now, hundreds of light years away. Exactly as astronomers continue to watch and record it, planet by planet, discovery by discovery, expanding what humanity understands about how worlds are born, how they change, and eventually how some of them come apart entirely. If two planets can transform this dramatically in the time it took Webb to simply watch them for one single orbit, imagine what else this telescope is quietly capturing right now, waiting to be discovered. Subscribe now so you never miss the next real transformation happening across the universe.